talking about the dynamics of the suspension. And today we want to get into steering, but just kind of a quick recap of what we did last time. So I'm going to share my screen. So what we did last time is we looked at kind of quickly a model of the car, right? Where we had a spring that represented the stiffness of the tire, right? To the mass that was unsprung, right? And so this comprised the wheel, the upright, all the spindle, right? And about half of the suspension arms and the shock typically. And then we had a spring up to our sprung mass. And we also had both damping, which does a force related to velocity, and a spring, which has a force related to displacement. And this is kind of what's called a quarter car model. So this is our quarter car model. Right? So we used like corner weights, you know, or corner masses for this case. And so we call this K of the wheel. So that's a W, and we call this C of the wheel, right? So this related the forces on the wheel to the displacements of the wheel, right? Or the velocities of the wheel, not the actual motion of the shock, right? So first we just looked at it here, and we made a model where we had Y of the ground was moving, right? So that's what we were doing last time. And a couple of things we said to design for to make your suspension, I mean, you want to keep your tire basically in contact with the ground, giving you the most traction as possible at all times. That's what we were looking to do, right? At some level, we're trying to also minimize the loads transferred to the driver, right? You don't want it to be too stiff, but with the racing vehicle, we were a little less concerned with that than you'd be with like a passenger vehicle. But so to do that, we said we wanted your mass unsprung to be small as possible, because that's what we're trying to control and keep on the ground. And we also want the ratio of the mass unsprung to the sprung mass to be as small as possible, basically, right? And so we said, so those are some designs principles, and we said, all right, first thing to get you in the ballpark is to look at your ride frequency, right? And so we said, first we converted it to hertz, right? And then we had a term for stiffness. So we had K wheel, K tire. So that's because, so you have this term, let's put them in the same order. K wheel, K tire. So this basically considers this to move this sprung mass, you have these two springs in series. So that's why you kind of have this springs in series term, basically. It's an equivalent stiffness. So this is basically K of the system divided by the sprung mass, right? And so we said to start, we put Baja in the like 1 to 2 hertz range, and formula was a little bit stiffer. We put formula is more in the 2 to 3 hertz range. You have this, they actually say this about structures too. So like the frame should be like 70 hertz stiff. You know, of course the frame's a lot stiffer than the ride, right? But so they have these kind of numbers to get you in the ballpark. So in this, the higher it is, the stiffer it is, right? And you can relate this to kind of getting the natural frequency when you sit on your hood, right? You know, 1 or 2 hertz on a passenger car, but we're quite a bit stiffer than a passenger car. And then we said to get the damping, because right, the thing that we're designing in this case, you know, we're trying to minimize this, at least, you know, the tire stiffness, we don't have a lot of control over except for picking our tire, but we completely pick our shock values, right? So these are what we're really trying to design for. So this gives us a value. So you said, you know this, and you know the tire, and you know your sprung mass, you can find the stiffness that you need for your wheel rate, basically, right? So this was our ride frequency, and that's in hertz, right? And then we said we had a damping ratio, which was the damping at our wheel times 2 times the sprung mass times omega the ride, right? And this was the damping ratio. And we said usually to start, this damping ratio be between 0.5 to 1. So that's called underdamped. And maybe like, you know, you can split the difference to start with 0.7. Right? So we did that and we said, okay, well, these were for the wheel. So, but we need to convert these to the shock, right? And so we said, hey, you have this lower control arm. So this is our lower control arm. Our wheel connects here, but our shock might connect here, right? And so it might have some angle. And so from perpendicular to your lower control arm. Keep in mind that line is not meant to be vertical. It's not meant to be vertical for gravity. It's meant to be vertical because it's at a right angle to your lower control arm, right? So this angle is measured off the vertical of your lower control arm. So if this is length 1 and this is length 2, you'll notice that when your tire moves up, your tire will move a lot more than your spring will displace, right? So in fact, that makes your spring act less stiff. So you need to take that into account. And so what we do is we do something called the motion ratio. So I'll call it MR. And I messed this up a few last time. It's cosine theta. And there's different definitions. Some people invert this, right? But so typically it's greater than 1, right? So if you're communicating with someone else on the team about your motion ratio, make sure you're communicating that it's the length of travel of the wheel divided by the displacement of your shock and not vice versa. And so from the above stuff, we figured out what our damping of our wheel was and the stiffness of our wheel. But to get the shock, to get K shock, we need to multiply that times the motion ratio squared times K of the wheel. So this is like the wheel, called the wheel rate. And then C of our shock, so the damping of our shock, would be equal to the motion ratio squared times C of the wheel. So wheel damping, right? And so the reason why it gets squared is because, like, for example, the shock is a force over displacement. So the displacement not only changes, but the force also gets changed by that amount. So you'll actually have a square effect. It doesn't cancel, it squares. So that's how we go from figuring out our wheels get us in the ballpark. So what we should do is what we did for a few folks who hung out last time, is we wrote a little MATLAB code to simulate a quarter mass system. So what I basically did is we have a little spot where I put in the sprung mass, so that I put in Baja parameters, the wheel rate, the damping rate of the wheel, the unsprung mass, and then the tire stiffness. I calculated for the ride frequency and the damping ratio just to compare. Keep in mind, one thing I did wrong last time actually is when I solved for the CW, I put in the ride frequency in hertz. Don't do that. This needs to go in as radians per second. You're going to be off by 2 pi if you don't do that, right? So make sure you put that. And, you know, dumb mistake, I made it yesterday, right? All right, so then here I determined what the motion ratio is and what the shock value should be. So these are not used anywhere else. They're just for my reference. Here's where I start to solve things. So I say I want to do a 3-second simulation, and then I discretize time. So I'm going to do 1 millisecond steps. So I'm going to solve for everything in 1 millisecond steps. I make a time vector. I initialize everything to 0. Right? I say my initial velocities are 0. And then here's where I prescribe different ground. So I need to say, what's the shape of the ground with time? And then what I basically did was I took this model up here and I said, all right, there will also be, I also said there could be a force on the sprung mass. So for example, if you have an aero package, there'll be a force on the sprung mass from your aerodynamics, right? So you could take that into account. So I added these variables even though I didn't use them, and the force unsprung. what I basically did is I made equations of motion. I said sum of the forces on the sprung mass equals to the mass times the acceleration of the sprung mass. And I had a force, basically, right? I have Fs plus I have a force from the shock plus a force from the dampener, right? And then I did the same thing. Sum of the forces for the unsprung mass is mass times the acceleration of the unsprung mass, which equals the force on the unsprung mass. And this one I have 3, right? So I have like plus like F of kW, F of K of the tire plus the force of the damper, right? So because this will have a force on the unsprung mass, this will have a force on the unsprung mass, this will create a force on the unsprung. So I basically said, and then I solved for the acceleration, right? So at every moment in time, I could solve for the displacement of the shock or the velocity, and then I went forward in time. So we can talk more. You can go and look back at the video about how exactly we did this. That's just what it kind of does here. I find the acceleration, and here I just integrate the acceleration. So I just basically say like, okay, the next velocity in time is equal to my acceleration times my little bit of time times my velocity. And I do that also for position. And then I plot some stuff. So I'm basically going to do, I did 3 scenarios. I did one scenario where we come and we hit a bump that's like 1 inch tall. I said, what will happen in that case? I said, what happens if I go to a tabletop where I ride up onto the tabletop? That's 2 inches. And what happens when I go off a jump that's 1 foot tall, right? So I said, so let's look at, so we can look at the response here. So I'm going to comment out, Control R. And so here's hitting a tabletop. Oops. So I basically, the way I make it hit a tabletop is I say the ground all of a sudden goes to 1 inch up. So we ran our simulation. So first thing we look at, let's look at the left plot. So this is the position in time of the sprung mass, the unsprung mass, and the ground. So the ground looks right. It goes from 0 to 1 inch. And this kind of makes sense to me. You go up onto a 1 inch curve. Eventually, everything will be 1 inch higher, basically, right? But what you see here is that you have your sprung mass gets hit up initially, and it goes a little bit higher, and then it comes back down, right? And the same thing with your sprung mass. So what you might want to do is let's look at how we can change some things. So so if we notice that our damping ratio is 0.9, that means we're somewhat under damped. So that means we should get some ringing, right? So let's see what happens if I go way less damped. So let's make it a quarter as much damping. So if we go like, we get a damping ratio of, it should be like, let's see here, 0.2. Look what your car does. So if you're too under damped, right, you come and you just oscillate, right? You don't have enough damping in your system, basically, right? So and then let's see what happens when we go way too damped. Right? So if you're under damped, it's like just a spring and mass. You start to oscillate a bunch, right? So here's our damping. Here's our damping ratio, basically right here. So what you basically see when you become crazy, when you become over damped, you basically just follow. It's basically like the top portion of your system becomes dead. So this top portion basically became dead because this spring is so stiff. And it's basically like you just have a mass on top of your tire, basically. So what we're seeing here is, so you basically have no overshoot. You basically, all your car does is it just follows your tire, basically, right? So that's not that good. That's not that good either, right? You don't want to just directly transfer it. So that's too much damping. So let's go back to what we had before. So here what you have before is you have it nice. You slowly come behind it and then you come back. But you could mess around with these values to get these here. The next thing I plot is the force on the total force on the sprung mass, the total force on the unsprung mass, and the force from the ground. And so you can see, we can start to make estimates of what are the forces on the corners of our car, right? So here's, for example, we're getting somewhere in the 300 pounds force on the tire, basically. So you can start to also get the forces. So we'll just run some of the cases. So I'm going to comment this part. I'm going to uncomment the ramp. So this basically is going to be a little ramp. So it shouldn't be all that different. It should be a little less of a, because it's 2 inches tall, I made it kind of ramp up onto the 2 inches. So you see the same thing, it kind of reaches the 2 inches. But because you go up a lot higher, you have a lot higher forces, maybe like 700 pounds on that corner, right? Let's try the last one. So I put this in there so people, you can change this to be something, you can change this and you can play around with it. So we'll run this and I'll show you there's something weird about it. So here we go off a big jump. So when you make a model like this, you need to be a little bit careful. So what you see here is you have the yellow is the jump. It goes up 12 inches, a 1 foot jump, right? But what you notice is your tire basically gets immediately pulled down into the ground. And the reason that is you go off a jump, but right now I'm not letting the bottom of my tire leave the ground in my model, right? This spring basically is hooked to the ground. So we need to do a little fix. So what we can do, for example, is I gave it this little part right here yesterday, where we said it can't accelerate more than -g downwards. We're gonna limit the acceleration down basically. So that's how we're gonna fix that little problem. And so what you see in this case now is you see the tire, it kind of initially gets hit with the ramp, but then it follows the ramp and it goes off the jump, right? So it comes down and at about 0.65 seconds, your tire hits the ground and squishes into the ground, right? And so you see from hitting the ground, right? So right here, you just have gravity's acting until 6.5, you hit the ground hard. And you see from going about almost, more than a foot in the air, you see about 600 pounds force, right? As you hit the ground, basically. Let's try going a little bit faster. Let's try going 30 miles an hour. See what it does to our car. So we jump a little bit further in the air, as you'd expect, right? You jump a little bit higher. Now we're jumping like 3 feet, right? So this is a good Baja jump. In this case, we come down and we hit at about 900 pounds. So this is like really extreme, a 3 foot jump. I mean, we've done it, well, maybe not 3, maybe 2 feet. So this is probably more than you'd probably usually see, right? But you can see how you can start to pair with other stuff to find the forces, right? So for example, here's some data where we measured the force, we measured the pressure we have little bicycle tire pressure sensors. And we're measuring the pressure of the wheels as we're driving around in a Baja car. And we've calibrated the change in pressure on the wheel to the force that it takes. And so what we've basically done is we take a moving average to find kind of our kind of baseline tire pressure, and then we find the difference between when it's getting hit. And the green right here is the force on the front, and the blue here is the force on the rear. And so you can see we're getting peaks up in the 500-600 range, right? So this is more info about what forces should you use, but they're pretty similar, about 5G bumps, right? So we have about 120 pounds on the front on these tires, right? So 5 times that's about 600 pounds. So, both cases are saying, 600 maybe 5G bump is not a bad case. Or we've also have strain gauge data, right? So we put strain gauges on the tires. I think this over predicts because, let me draw a little schematic. So because the strain gauge is on the spindle of the tire, and here's your wheel, and it sits like here. I mean, it actually sits closer, and it measures the moment. So it measures the force times the length. But we basically kind of have to assume the tire is actually wide. The tire is 7 inches wide. So we have to assume, we just kind of assume it gets hit in the middle, but you could actually have big forces that are much farther on the outside, which would give you a lot bigger moment, right? So I think that's what's happening in this data. And that's why you see we go up to a little bit higher. We go up to maybe 1,000 pounds force. But I think that's an error in our instrumentation maybe. This might be a little bit higher than we expect. So I think maybe the other data is more reliable in the 600-700 pound range, kind of the 5G corner range. But putting all that together, you can make an argument for the judges about why you pick the different forces for designing your different components, basically, right? And this can help you get, something like these quick calculations can help you figure out, okay, well, what should my shock stiffness be, right? So that you're not going and just buying random shocks off the shelf, right? This will get you in the ballpark before you do some testing, right? This is a model, it's not right, but it gives you some information to get you in the ballpark so you can start to tune around that value, basically. So that was basically kind of a little summary of kind of everything we've done up to this part, kind of bringing it all together. And you can see, it's not critical to get the right damping ratio and stuff, but to get the right responses from your car, right? And the other thing we wanted to make sure is that you can also, in like models like this, for example, you could have your stiffness be a function of the displacement squared. So you can model nonlinear stuff, right? Which you couldn't do it's really hard to do with analytical solutions. So for example, our springs in our steering system, so like Baja, right? The way our springs behave are these curves. They're not linear springs, right? So if you wanted to actually model a spring, they're actually nonlinear, which is good because you want a progressive spring so that you don't end up bottoming out, right? So progressive's good, and you either do this with two springs, air shocks, or your motion ratio can change. So we talked a little bit about that last time. But if you want to see more about how to get this progressively stiffer, because you want it soft down here, but when you get near the end of travel, you don't want to smash into it, right? So you'll have bump stops and you have progressive springs. So with that, let's get into a little bit more about steering. So steering. So we need to talk about, we need to talk a little bit more about the geometry of the car. So if we look at our tire from the rear, and this is the right tire, let's draw in where our two ball joints are for our upper and lower control arms. So maybe we'll have one here, and we could have like one here, right? So your tire, when you turn your tire, it rotates about those 2 points. So your tire rotates about this axis, right? So when you turn your tire, it rotates about this axis. So we call this the steering axis. Right? So the angle between vertical, so let's say this is vertical, we'll say our tires is like this. So this is, I might exaggerate this a little bit more. So this is vertical. This is your tires axis. So this angle right here is your camber, right? So so we're looking from the rear at the front right tire, right? Basically. So I should say looking from here. At front right tire. I'm just trying to say kind of what we're, so visualize you're kind of looking from behind at that front right tire basically, right? So that angle is your camber angle. And then the angle from here to here is your kingpin inclination angle, right? So you typically want a little bit of kingpin inclination. So you want your KPI, you know, I don't know, books say like in the 5 to 10 degree range. And what that basically does is you imagine when your tire needs to turn, it needs to dig into the ground, right? For your tire to basically turn. So imagine pulling this tire towards you, because that kingpin angle is kind of over here to the right, it's kind of angled to the left. It digs it into the ground. So that helps you give some stability in your steering, right? So this provides stability. Another thing you look at when you're designing your steering is your scrub radius. So the distance from here, so the distance from here to here, this is your scrub radius. So imagine when you turn your tire about that axis, this tire needs to scrub across the ground along that axis. So for formula, we typically want this pretty low. So your scrub radius, you know, maybe 0 to 1 inch, right? You want to make it easy to turn. You just want your tire to turn about its own axis, right? So you don't want your tire to actually have to move along the ground when you're turning, right? Otherwise, at like slow speeds, it's really hard to turn, right? So 0 to 1 for FSAE. Baja, we do them a little bit bigger. So maybe like 1 to 2 inches for Baja. Dan and Blake talk a lot about weight shift when you're steering. I mean, they've built a lot of these cars, and so so I think there's something to it. I don't know as much about it, but as you kind of steer, imagine a right-hand turn. If you have this scrub radius and this kingpin inclination, your tire kind of digs back down into the ground, your front right tire, right? It shifts your weight to the back left, which helps you kind of kick around. That's kind of the argument for it. In Baja, we actually don't steer much with our rear. We actually drift a lot at high speed. So I'm not sure how much of an effect that really has, or if it's more just it provides more downforce on the front right wheel. We're turning more with the front right wheel, but it's worked. They've used this principle and made cars that turn nice. So you know, that can't be completely ignored. All right, so we talked about scrub radius. We talked about kingpin inclination. The camber, remember, we always want our wheel vertical, right? We don't want it actually tilted like this. The wheels get best vertical, or a slight camber in maybe for turning. Okay, so the other thing we need to do, the steering is tough. There's 1,000 different angles to keep in mind here. So, and distances, but we're just gonna kind of go through them. So now we need to look at this tire from the right side. So this is the front right tire again, looking at it from the right side. And if we draw these two points again, here and here, we can look at our steering axis in this plane. So this is our steering axis. So this angle here anybody know what this angle is?
Caster?
Yeah, that's our caster, right? So this is your caster. So this does something similar. Does something similar to your kingpin inclination. So you typically want, you know, the same thing, you know, 5 degrees of caster on these front wheels. One, so that when you're so that when you turn it, it like comes back into the ground basically. So it has a kind of that similar effect. But more importantly, what it also provides you is if you go from the center of your tire to the front, this length is called trail. That's the trail of your tire. And you want positive trail. So trail needs to be greater than 0. Caster angle would also be, you know, on the order of 5 degrees, I would say. And the way to think about trail is think about like a shopping cart wheel. That's the classic, that's like the biggest trail scenario. So you got like a shopping cart wheel. It'll pivot, oops. It'll pivot about this point, and it comes down and it holds the wheel right here. Right? Your shopping cart wheel. So this is where your steering axis meets the ground, and this is your trail. So when you back up, right? Imagine backing up in a shopping cart, right? The wheels flip around. Now imagine trying to drive it for a little bit right then. Like what happens when you start to drive it with the trail when you've turned your shopping cart wheels the other direction?
Shifts.
Yeah, they like for a little bit you don't even turn right. You like can't control it until they flip around, right, and get into their stable position where you have trail, right, and then you can steer it, right. So if you design it, right, so if you design your car with, you know, a big caster and like ending up down here, you've made a very unstable system basically. The tire rotates about that point and the forces can push it left and right and forces it to turn. So this is really hard for the driver to hold on to because it's very unstable. So you need a little bit of positive trail, right? I mean, the nice part about a shopping cart wheel is it's designed so the wheel can spin around and give itself trail. But in your case, you're kind of constraining that. So don't constrain it wrong, basically. Because the driver has to hold the steering wheel in your case, right? So that's trail. All right, so let's look at how some of this will affect the tire and its interaction with the ground. So what I've basically done is I've made a tire and I've made the ground and I've drawn the steering axis, you know, also known as kind of the kingpin axis, but it basically would connect the upper and lower ball joint. And you draw a line between those two, right? Obviously I intend them to go through like these two spots on kind of a fake kingpin sticking out, but this one I wanted to show a case where, all right, let's first start and just look at kingpin and scrub radius. So as you can see, since the steering axis comes and it intersects right in the center where the tire touches the ground, that we have no scrub radius in this case, but because the axis is inclined, we have a little bit of kingpin inclination. So what I'd like to do is I'll take it this way, and you can see right now the tire is just touching the ground. And what we can do, we lift it up slightly, and let's pretend like we have a tie rod here, and let's, oh, I forgot, I need to undo two mates. Suppress that mate and suppress this mate, and then we can rotate it. Right. So let's say, you know, this is the, and so you'll notice that this is intended to be in the rest of the demos. This will be kind of the front side, and this will be kind of the back side right here. So the tire's traveling over on the right side over here. So if we look now down, you'll see that what you'll get when you have some kingpin inclination is your tire will subtly start to go into the ground when you go forward, or let's see what happens. So from this, the front left wheel, I guess. And so that's making a right-hand turn, or to make a left-hand turn, it also goes into the ground. So in both of these cases, it pushes your tire, it basically, your tire is basically pushing into the ground. And so in both of these cases, you basically have to lift your car up in the air slightly. And so both of these are not going to be favorable. And so what ends up happening is this provides some kind of self-centering of the wheel. So, and some kind of straight line stability. So having some kingpin inclination is good for doing subtle, a little bit of that. So, you know, for example, when you're driving on the steering wheel and you let go, the steering wheel is naturally going to go and the car is going to just return to straight, right? So having some kingpin can do that. So let's also, and you see it's just very subtle though when we have no scrub radius. So let's also add a little bit of scrub radius. So I'm going to go to the tire, and what I'm going to do in this case, so I'm going to move this point on the ground. So let's add a little scrub radius. So let's add 3 inches. So I'll add, or maybe even 4. So we'll move out the Z to 7 inches here. And then the top point, we'll move out, and we'll keep a little bit of kingpin inclination. And we'll move the top point out maybe to 12. So we'll set our kingpin axis like this. So here, let's exit my sketch. Right, so you can see this is where the upper ball joint would be, for example, and the lower ball joint would be. Let's update our assembly. Yes. And let's unsuppress these. That way it'll re-straighten our tire, and we'll suppress them again. Okay. So you can see again our tire's flat on the ground all the way across. You can move the ground a little bit more, be in the middle. Oops, I shouldn't have done that with everything unsuppressed actually. So we'll leave it here for now. And so I'll try and massage it to be straight. And let's lift just up a little bit. And let's see what happens when we do a hard right-hand turn. You see now with the scrub radius, it's much more pronounced how much the tire is going down into the ground basically. But as you turn in both directions, that direction, or you turn it back, it's going down into the ground, right? So the scrub radius and kingpin inclination definitely interact together quite a bit to do this. So it's not just one or just the other. You have both, and that's why we typically recommend 5 to 10 degrees of kingpin inclination, and an inch or two of scrub. I mean, the other thing you'll notice though is now as you turn, the tire does scrub across the track, right? So if you're going slow, this might be kind of add some tire effort, although I don't think it's going to be super appreciable. The kingpin inclination, if you have too much kingpin inclination, I mean, you're literally raising and lowering the car as you turn, right? So that's going to add more steering effort. So the other thing that will happen is you imagine now that you have so the other thing, so basically kingpin inclination, right? It helps for high-speed stability, self-centering, because when you turn in either direction, it goes down into the ground. But it adds tire effort. It adds steering effort because you literally have to lift the car up as you turn the car, and it's going to move your CG up, right? So in a turn, it's going to move your CG up, and you also see it also brings your tire down on edge, right? So it also kind of will add some camber to your tire in a turn, right? So there's all of that to contend with, and then the scrub radius. The scrub radius is known to give the driver a little bit of feel. So now you can think about it. The forces in the tire are acting around this axis. So whatever's holding your toe, for example, in the front would probably be like a tie rod to your steering. And in the rear, you might have like kind of some toe link. The more scrub radius you have, the more load that's going to go through it, especially on braking, for example. So braking is going to be large forces back, right? So if you have rear steering connect to the rear, you're going to put your kind of long tie rods in compression, which might not be favorable. It might even be favorable to have front steering in that case to pull them in tension if you have large scrub radii. But the scrub radius is known to give the driver some feel. I'm not sure it's exactly the physical mechanism behind that. Probably has, again, something to do with transferring these forces to the steering wheel and to the driver in this case. Whereas if you have your steering axes go right to the center of the tire, a lot of the forces on the tire are going to be held by the suspension members and are not going to be held by what holds the toe. So the driver is not going to get quite as much feedback and feel, which maybe isn't as important for our autocross, just because you guys are going quick in and out of turns. You're not really trying to find the very edge. And so keep that in mind. So okay, so that's kind of the kingpin inclination, ups and downs, and scrub radius and how they interact together. So let's look a little bit now at the effects of caster and trail. So I'm going to go back into my tire. I don't know why I call this the tire, but anyway, so we're going to go back. Let's edit this. Edit the sketch. I'm going to pull this point in front to give us a little trail. So maybe give us 3 inches of trail, right? And then let's I'm going to come into this line. I'm going to move this back. So let's do -3. Make sure that's what I want, right? So okay. So now if we look in this direction, I'm going to exit my sketch, and you're going to see top ball joints here, lower bottom joints here, right? In this case, I've kept with having a little bit of kingpin inclination as well. Although maybe we can get rid of that for now. Let's simplify so we can look at just one effect and not 2 effects. So I'm going to take this. I'm going to put this straight up and down. So we'll put this at 7. All right, so we have a little bit of scrub radius, but no kingpin inclination. We can, if we want, we can even, if we have a little bit of time, let's just do caster. We'll do no effects in that direction. Okay, so obviously our kingpin inclination is kind of 0. Our scrub radius is 0, but we have some trail and some caster. So we'll just look at those together, since they're pretty much always going to go together. Then, of course, there are ways you could do it where they don't go together, but okay, so let's unsuppress this, unsuppress this mate. Right, so we got our tire. With them flat, you can always move this around. So I'll put this in the drop box so you can play with the model a little bit. And let's suppress this, and let's suppress that. Okay, so at this point we have some caster. Now let's see what happens when this front left wheel makes a hard left turn. So if we look, the inside of the wheel kind of digs in a little, but the outside lifts up for the most part, right? And you also see you get some pretty good camber in your tire as you do that, which is probably not a great thing. Here, your outside tire comes in, and it makes contact, and this lifts up. But there's not much appreciable difference between going forward or back. It looks like they both go into the ground. So having so you do have the advantage of the trail, where you're now steering is at least stable. It's a little easier to rotate this about if you're up higher. So it's at least stable now, and that your contact patch is behind the axis, right? And we talked about that with the kind of the shopping cart or kind of caster effect. So let's go. So we see it doesn't have as much of an effect with without any scrub radius. So let's add some scrub radius to this thing. So we're gonna go back into the sketch, edit the sketch. All right, so we're gonna pull this out to 7 inches on the Z direction. And then I'm gonna take this line, I'm gonna add, this one's gonna come out to 12. All right, so now we're looking good. Now we got a little bit of
we got our caster, scrub. Ooh, let's do, I forgot, let's do no, let's just add scrub, but let's not add any kingpin inclination yet. So 7 and 7. Okay. All right, so you see we have the caster, and we have a little bit of trail, and we have a little scrub radius as this axis hits in front. So now let's go to the wheel assembly. We'll remade it to put it flat on the ground. Looks good. And then let's suppress these so that we can now see how they relate. So now let's see what happens. Hard left-hand turn. Interesting. This is the first we've seen this, right? The tire comes off the ground in this case, right? So in this case, the left-hand turn comes up. All right, let's try that's a right-hand turn, it comes up. Left-hand turn, that thing's swinging down into the ground down there, right? So this is one of the big reasons to have some caster. So, okay, so for example, right now, you're making a right-hand turn. So what this does, because this tire lifts up and the opposite is going to happen on your right tire, it's going to go down into the ground. So what that basically does is it's going to lift, your right tire is actually going to move up a little bit, compress the spring, and it's going to weight shift. So it's going to shift weight. So it's going to move the right tire up. It's going to compress the right spring, right? As it needs to go into the ground. On the left tire, because it's kind of naturally coming off the ground, it's going to allow the spring to stretch out basically. And so what that does is it's going to shift weight from the front left to the front right. If you can imagine that, which is great because you're making maybe a hard right-hand turn, and all that weight shift is coming to the front left, and you want to unload that, give some back to that front right, and it's counteracting some of the roll. So this is great. This is, maybe even more beneficial than the kingpin inclination in a turn, right? Because you're actually giving you the desired weight shift that you'd want to give you better handling. There are some additional effects that this kind of messes up your weight shift in the rear, though. So we'll show a little bit more about that later. And this is better than, for example, the kingpin inclination, right? We noticed that it lifted our CG up as we turned, right? Which isn't great in a turn. So this caster with a little bit of scrub radius really helps put that weight down on the front right tire. I think this is a kind of a lot of what's happening, I think, in the Baja car, and that what you'll see is that when we do a lot of this on the Baja car, we give quite a bit of caster, quite a bit of scrub radius, and when you turn to the right, you'll have additional weight on the front right wheel, and you also see additional weight on the back left. So if you picture it kind of a square, maybe let me allow some annotation. So we looked at the top and we looked at 4 wheels, right? So this one's going to lose weight, do a minus sign. This is going to gain weight. This is going to gain weight. This is going to lose weight, which when you're making a right-hand turn is good to a point, because typically what that's going to do is that's going to shift weight forward and to the left, basically. And so this helps shift a little bit back to the right in the front where you need it. But you'll notice the downside is it gives you more weight shift in the rear. So it basically doubles, it doubles kind of the weight shift in the rear on a right-hand turn. But so you might, this might be from the caster, this is from weight transfer. And in this case, this is from the caster, and this is from the weight transfer. So it cancels out some of the weight transfer in the front. So like for Baja, I think, we've talked a lot about how, doing this will help put weight on this wheel and kick it around. I'm not sure if that's necessarily the case. I think it's more that it pins this front right. It kind of pins this front right wheel on the Baja car, and you have so much weight transfer in the rear that you begin to have a lot of oversteer and begin to kind of lose grip in the rear. And that's why you kind of spin around this front wheel, which helps in these kind of tight turns that you have, especially we have this locked rear, right? And so it's really hard to turn that anyway. So typically you just want to lose grip and kind of swing around on you for a sharp turn. So that's kind of really important to understand about the caster. And I think the purpose of having, 5 to 10 degrees of caster as well. So let's click on these. But you'll see kind of some of the downsides, right? So one, as you start to come way back here, you start to have large camber of your tire, right? You're gonna start to roll on just one edge. You just start to ride on kind of the outside edge of your tire, which, so to a point, is not great, right? And I think naturally having some caster is just kind of critical, just to make sure you have some trail, because you just go crazy unstable when you don't have any trail. Especially imagine when you have some pitch forward as you're stopping, you just want to make sure you continue to have some positive trail even in those cases. So I think having some caster is even just important for that, even though you could have zero caster hypothetically and have trail like in a shopping cart or a caster. So let's just look now that let's try let's go back and let's give ourselves a little bit of both. So let's see the full picture at this point. So no, not the right one. So we need to edit this. Right, and so this one's actually good. I just want to move out the top. Right, so I'm just going to move out in the Z direction, move out to 12 or so. There we go. So now this is probably what you're typically going to do. You're going to give yourself a little bit of caster, a little bit of kingpin inclination. Obviously your mounts off your kingpin are going to look like this. They should not be in bending or not be partially cut, but I think it's just so you can kind of try to make it so you kind of see a visual of kind of imagine this is where your upper and lower ball joints are. Okay, so let's redo this. All right, thing over here. We're just going to suppress these last two mates. Okay, and let's see what happens when we make a left-hand turn. So you see here the caster has a larger effect than the kingpin inclination. Because you remember kingpin inclination typically brought both tires down into the ground, right? And whether you turn forward or back, caster was actually one where in this direction it lifted it, in the other direction it brought it into the ground. And so you can see that I think just partially because the parameters I put in, I probably have more caster angle than I do kingpin inclination. And so kind of showed that this had this effect. I think if we made the caster very small and the kingpin inclination very big, and also messed with the trail and the scrub radius, then we could have seen the opposite effect. But this is probably what's going to happen in your car. And this turns back, and so as that turns back, it really dips in. So we're seeing a little bit closer to kind of having the case with just caster, which is probably, that was the thing that was slightly more advantageous. So that's probably not a terrible thing. And keep in mind, so it's kind of, there's some analogies between the trail, right? It's kind of a moment arm, and the caster, it's kind of an angle related to that moment arm. And then, so that's like in this direction, right? So when we look at it from this direction, so let's just bring everything back. All right, so if we look at it in this direction, so caster is the angle here, and trail is kind of the moment arm. And when we come and look at it in this direction, scrub radius is the moment arm, and the kingpin inclination is the angle, right? And you see how, because the tire is here, and this steering axis comes down here, the distance from the center of the tire to where it comes in is affected by both the scrub radius. So in actuality, you actually notice that kind of the trail and the scrub radius will kind of play together a little bit. And I think that's kind of just an important thing to note with all four of these, for example, is that, you know, there's no kind of set numbers for any of them, and that you can't just say one should be this. You know, it's really all four kind of interplay together. I mean, I would love to have a car where these were crazy adjustable and we could do lap times and do a whole matrix of them. I think unfortunately we never have enough time to do that much testing, but I think it's, you know, to get, you know, more precise numbers and kind of, hey, what's this kind of just the practical advice I've seen from folks, which makes sense with the physics that we can see, without kind of more extensive testing. Actually, it's probably in the SAE literature. If we got off our butts and really did some digging, we could probably find some good data. But you can see just it's an infinite number of things to test almost. So yeah. So well, now hopefully now you can see at least what'll get you in the ballpark for these values, and where to start off. So let's look at maybe one last thing, which would be kind of interesting, which I don't even know what's going to happen. Actually, I'm kind of curious. What happens when you go to a negative scrub radius? I mean, we know we can't do negative trail; it's just crazy unstable. But what about negative scrub radius? Let's see what happens in that. Okay, so I'm going to get rid of the caster, so we don't see that effect. So we're going to bring this x value to 0. We're going to bring the z value to maybe like -1. Good, so it's in the center of the tire and back. Okay, and then we get this line, and we bring this to 0. Maybe this to 5. Right. So let's go and check it out. So let's see what happens. I've heard of people running the negative scrub radius. Never actually seen it. Let's see what happens. So we're going to suppress this. All right, so let's turn our tire. So it actually comes off the ground for the most part. Let's turn it all here. Hard part is there's also camber. All right, so I think it for the most part comes off the ground. I mean, the average location is actually further away. So this is probably, it seems to me from a steering point of view, this might be undesirable, because this kind of is allowed to go up. It'll actually allow your it's actually kind of gonna allow your car to sink down a little bit, which will kind of lower its overall potential energy, right? So I feel my intuition here, which I don't know if it's right, but it seems like this would be slightly unstable. It seems like you wouldn't have as much of a natural steering return, whereas before we knew that the kind of having some kingpin inclination and the scrub radius, the tires dug into the ground, and so it made them go straight. Here it almost seems like the opposite effect. So that seems not advisable of a thing to do. But again, all these things play in together, right? And so you might check, see maybe this somehow decreases some of the, can counteract some of the bad things that happen as you use more caster. So maybe doing this could allow you to go a little more extreme on the caster and so forth. So anyway, so I think that's interesting. And I want to show one quick video, which I think is really good, and it shows all 4 of the wheels. So this guy makes me crack up. So it's Smitty and the professor from UCI. These are actually good videos. They're nice and short and sweet to the point, and he's got great visuals and demos that he's built. You know, took me an hour to build this in SolidWorks. I'm sure it took me a lot longer to build this physical one, but I would love to get my hands on it, be able to play around with it and look at it, because I think nothing better than give you intuition than to be able to adjust it, right? So let's take a look. He has kind of, this is the 4-wheel, kind of a 4-wheel setup with scales, right? So let's look at the full thing.
So the other dimension that we should talk about is so this is a top view. So this angle is your toe, right? So typically, so this line is meant to be forward and back, and this angle from straight forward and back is your toe, basically. That's such a bad drawing. Get rid of this wheel. This is the center of your car, and then here's your wheel. Here's vertical, and this is your toe, right? So typically you want your wheels pretty neutral, like 0 toe. And if you're going to err on having a slight bit, I would err on having a slight bit of toe in, just because it's more stable. The wheels were self-centered, right? So toe should be around 0 degrees. Err on slight toe in. Right? They'll kind of self-center, right? To even themselves out. So you err on a slight toe in. I've heard some arguments for in the rear. So keep in mind, you don't really have as much of a steering axis in the rear, because usually you don't let your tires rotate at all. But you still have so you don't really have caster in the rear, but you have toe in the rear and you have camber in the rear, right? And these can change through travel. So like Baja, for example, sometimes they try and get toe in travel, right? So that, for example, as the tire goes up, like think about making a right-hand turn, as that weight gets shifted to the back left, there's been arguments to have that back wheel as it travels up to toe out to kind of kick you around the turn. I mean, I'm still skeptical about how much turning is ever done by the back wheels on our Baja cars these days. Maybe in the past they used to have kind of wider in the rear, but these days we totally drift out that rear on tight turns, basically.
Is the track the same? The tracker wheels the same for the front and the rear for Baja?
No, and we'll talk a little about this, but we typically run a smaller track width in the rear to promote oversteering, so it's easier to lose traction in the rear in a turn. So typically we make the front a little bit wider than the rear.
Because I've seen teams on Formula, they do that because they say, like, I guess somehow it helps with the front grip, or like something like that. After looking at it, and
Yeah,
then also,
I mean,
as far as the caster in the back for Formula, I feel like it should lean more towards like a shopping cart, or if anything, that could possibly help like it could help keep your wheel straight in a sense. Instead of going like positive, you could go negative.
yeah. I mean, I guess you're a little bit right. So you don't normally think about the caster as much in the rear, but you do have the upper and lower ball joints that can rotate around, right? So you don't normally rotate it around those because you keep it fixed. But I suppose you could try and keep having a little bit of trail in the rear. I think that's a good point, David. A little bit of trail in the rear so that it's a little bit more stable.
Because I've seen like USC, I think, for example, they have trailing arms, but like Or they have like a yeah, this one with the trailing arm like Baja, but their top A arm is on the front side of the wheel. So then when you draw that line between the connection for the top and the bottom A arm,
Yeah.
it's gonna be like a negative caster.
Interesting. I mean, so when you look, so if you like, you're kind of talking like, so this may be the back left wheel. You could maybe have more of this setup. So you see some teams, so this is the top view, right? The top view, and then here's maybe a side view. And this is the front of the car, here's the rear, this is the back left wheel, so this is the back left wheel. And so maybe you have something like this. People kind of, so yeah, I mean, that's a kind of a more kind of old school setup, right? So this avoids, this is kind of an anti-jacking setup here, because this will go towards your CG. So we talked a little bit about last time how you can have jacking on the side view, which is good. It's also nice because your tire moves in like this direction. So if it hits a bump, it kind of comes back. This top view packaging is also nice because instead of having equal arms like this, now you need to have a mounting point way back here. So you need your frame to extend way back if you want to get the wheelbase. So you can make your frame smaller and connect here if you can get that point. But I think you probably, if you look at your rear wheel, so here's the front of the car, and here's the rear of the car, and here's the back left wheel. You probably still want the steering axis to come down in front of the contact point, so you have some trail, right? So the contact point should be behind what it steers about for stability. I mean, that's a good point. So there kind of is caster in the rear. You know, you don't talk about it as much because you don't actually turn your tires right too much. But that's an interesting question. It'd be interesting to look up to what people have done if they think it's an issue. Because it's just your toe link, right? Your toe link holds. You have a toe link in the rear that holds all this. All right, so let's get it. So okay, so that's just a little bit of the steering, just kind of like tire angles and stuff, right? But let's look at the top view of a car. In a turn. So here's your rear wheels, right? And let's say you want to turn about this point, right? So your rear wheels are turning about this point. So your front wheels, which maybe the center's here and the other center's here, they need to also be at a right angle to this point, right? So this one is like this, and this one is like this.
Oh, real quick, I think what their argument was is that since the front of the car weight transfer happens before the rear tires technically, I guess when they reduce that distance, it happens evenly.
Reduce
somehow,
which
like
distance?
when you're going into a corner, that like somehow with that it stabilizes the car, something like that.
Yeah. I mean, so yeah, in a corner, you're typically decelerating before it, so you have weight transfer to the front. I mean, if you have weight, so you have weight transfer from back to front, and let's say you're making a right-hand turn, you have weight transfer right to left. It depends on your setup, which one, if you have more weight transfer in the front right to left or in the rear right to left. So that's like now we're talking about a pretty dynamic situation, right? We haven't been
Then I feel like, I don't know, like that, if they reduce the track width in the back by like, I don't know, like.
Oh, you're talking about the track width scenario. Oh, yeah. I haven't I'd be curious. I haven't seen a lot of reason to reduce the track width. But okay, so we're in a turn, right? So this is what I would call like the turn radius. I don't know. I mean, you could do it from the center of the car, but I usually like to think about it curb to curb. You know, if you had two curbs, you know, one on the far left over here and one on the far right, you know, could you make a turn from curb to curb basically, right? So that way you know, it's more has to do with the track than necessarily. Otherwise, if you just do center to center, I don't know what kind of turn you could actually make. You know, I care about what turn can your car actually do, you know. Does anyone notice that the front right tire, the inside tire, it's at a steeper angle than your front tire, right? So you need to make a steering system. So this is theta plus some delta, you know, delta theta, right? So this is extra turning on inside wheel. Right? And you notice this radius is shorter, right? So this tire is actually spinning faster. Same, this tire is also spinning faster. So that's why you have a differential in your car, right? So in a turn, these tires are spinning faster than these ones. And so if they're locked together, it's not going to turn very well. It's going to skip. So that's why if you ever put your truck in like 4x4 mode and try and drive on a parking lot, it's going to like, it's going to skip a bunch, right? So that's why you use diffs. So this is kind of complicated. How do you get it to do this? So this clever dude, Ackerman, came up with a way to do this. So kind of the classic is this Ackerman geometry. So you have your tires. And then these, let's say this is your steering axis. This is your steering axis, right? This is this center of rear axle. So remember our steering axis, that's our tire turns about, right? So you draw a line from here to the center of your rear axle, okay? So in kind of the old like the old buggy days, what you'd have is you'd have some upright here. And what you do is you connect your steering arm. So typically so this is your upright. And this is your tie rod connection. And this will connect onto a bar that comes onto here. So you have a steering axis here. It does this on both sides, right? And so if this bar that you hook up connects at a point along these lines, you're going to naturally get Ackerman steering. If you connect outside here, like in this area, so this is Ackerman deficient. This area here, so it's on both sides. And typically you want this to be symmetrical on both sides. So this is excess Ackerman. Right? So you don't typically set it up this way though, our teams, right? You don't have this old one bar goes to both wheels and then you just move that bar back and forth, right? You know, they'd have like, you know, your steering wheel would be here and it would have some steering arm that would come on here and it would like, you know, rotate it back and forth, right? So it's some old school. So we use a rack and pinion, right? So basically what our setup's gonna do instead is we're gonna have a rack with a gear on it. This rack travels left and right. We have our steering axis. Typically this little part, we call this like the steering arm if it sticks off. At least our teams just call that a steering arm. So you have a rack and pinion. Your rack moves left and right. Sometimes, so here's our steering axis. And then you'll connect between here and this point, it'll be your tie rod. And that'll move, and so that's how we typically move our system left and right, basically, right? And sometimes, if it's just a part of the upright, you know, it's just a part of the, it's basically your tie rod connecting point, you know, but it's basically, a lot of times when we refer to it, it'll be like, where does the steering arm connect with the tie rod, right? So we don't just guess with this stuff. So we're engineers. We'll at least try to be intelligent. So we'll make a little model, right? Let's get us in the ballpark. You know, let's not just build something random. Let's build something that we think is as close as possible and see how close we can get. Okay. So here's a model of our car. You can see the back left tire, the back right, the front left, and the front right. There's very few things you can actually change in this model. I did this on purpose in SolidWorks. So don't worry about opening it yet, just watch. But I said you can change the track width, right? So I could go like, you know, I could change the track width. I'm not gonna change it right now, actually. I can change the tire sizes. I can change the wheelbase. This 25. This changes where the center of your rack is. I can change my rack length. I can change the position of my rack forward and back. I can change where my steering axis is. Right here. So right now it's 4.5 inches from the center of my tire, but even vertically. And I can change the angle and the length of my steering arm from the center of my tire. And I put in a center line here so I could see that I'm in excess Ackerman right now, right? And I've also on this side, I've drawn a 60-degree triangle so you can see if our side of our wheel begins to hit one of our arms, right? And the rest, like your tie rod length, it all gets calculated, right? So ideally you should make your SolidWorks models like this so that everything else is calculated. So like, for example, all my tires, I change this tire and it'll change everything, right? So, and we'll see here, I'll probably find some stuff that's wrong with this. But like, you know, so that changes.
Could you change the distance from the center of your tire to like that distance? Can you like make it off center?
Forward and back, the steering axis?
Yeah.
Yeah, we could. I didn't program that in yet in this model.
Or like for caster, I guess.
Yeah, I mean, so you could have caster with this as your average steering, but yeah, you might want to move it off. But for example, I need to fix like the distance from here to the front and the distance here to here, so it rotates the tires. But so the nice part about this is, so we can look at our current setup, and let's move our rack 1 inch to the left, so 24. So you can see my inside tire moves at 11.74 degrees. My outside tire moves at 9.52. And you can see my turning radius is 220 inches, and it's slightly in front of the rear, right? So that has excess Ackerman, right? And what you'll start to see is, let's go to 23.5. And you see what I begin to get limited by, right? So my turning radius depends a lot on how much I can turn my two tires. So right now it's, you know, I'm at 131 inches on this turning radius for this turn, but what's starting to happen is you can see as the rack moves to the left, the tie rod right here and the steering arm begin to go over center. So that's what we call over center. So you should have a stop so that these do not go in a straight line. Because you imagine now when you try and go left, it just gets stuck. So right now we didn't hit here. We just got stuck, right? We just got stuck right here. So this is probably the best we can do with this setup. Go back to 25, right? So, so let's see what happens. Let's see what happens when we go Ackermann deficient. So let's make this like 5. So now my meeting point is over here. Maybe I'll go like 6. So I'm slightly Ackermann deficient, right? I'm not on the line here. And let's see what happens now. So 24.5, give it a little turn. 24, I give it a little more turn. I'm almost already at straight line, and you'll notice your model will blow up. Like, so if you just come in here and put 23, oh, well, you can see it went over center. I might regret blowing this thing up. There you go. So at some point I'll say I can't even do it, even if you go over center. So let's go back to the 24 where it was about straight. And so you'll see in this case, our turning radius is about 325. That's where they kind of all meet, roughly. And you'll notice we're kind of Ackermann deficient. Our turning radius for our 2 front wheels is meeting behind where our back 2 wheels will meet at, right? So that's because so let's try and get perfect Ackermann. So let's come in here. I'm going to put my steering axis right on this line. So like right at 7. Just a little bit more. 7.1. 7.2. All right, so that's about as close to that line as I think I can get. Right, and so now let's try turning our tires. It's pretty straight. So here I'm still a little bit in front, right? And we can go back. Let's see here, and we'll see how in this case, because we have a rack, we move this to like 1 inch. So we'll move our rack closer up to the center line of our car, basically, right? So now our rack's up here. We still have the same Ackermann. Let's go to 24. Not even meeting yet. So here we can go a little further now. See, are we going over center yet? Nope, not yet. So now we got 2 inches of travel on our rack. 23, 22. So now it's about to kind of go over center. So now you can see where our tires meet. It meets way back here. So we predict to have Ackermann, right? But because the rack position actually does matter, right? So you don't just assume that because you got this meeting point right, that everything else is right. That assumes that your rack is like actually, so it would maybe be like 4.5. Your rack is actually kind of in line with this, and this moves as a bar, right? And you should also keep that in mind. So for example, if you so the reason why we could turn more in that last case, so if I go to like 8, let's go to 10. You'll see in this case, this is like a bad position for my rack, right? Because at this case, my tie rod, it's already going over center with the steering arm. And I haven't even moved it. So like this setup, you can't even turn your tires. right? It's just a bad setup, right? It's also bad because you essentially, so this is the moment arm, so this is what it's spinning about. So your tire's spinning about this point, and you're pushing here. So ideally, you would push along this axis, basically, right? So you want to push like right along here. So you don't want to be, so you want to be, right? You want to be pushing normal to the moment. Anytime you're trying to make a moment, you want to push normal to it, right? So here we want to push normal to it. So we want to move this back closer to like maybe 3 inches for this setup, right? And that way we're pushing a little bit more normal to the line between here and here. So yeah. I mean, you're really, to be honest, you're kind of pushing left and right along the rack here in the end. So you're actually always kind of pushing left. You're always kind of pushing left. This is an interesting question about the forces in the steering. So if you're always kind of pushing left.
This is rear steer or front steer?
This is rear steer, right? Because you're hooking up
Behind it?
on your steering arms behind your steering axis. A front steer car would be come up to the front. So Baja does a front steer. Yeah, the front, so you could do the same thing, but you could hook in the front. Front steer, actually, you can usually get better turn angles because
that's what we
now
have.
you can see we're already kind of in line with our, we're already kind of in line with our, yeah, with our steering arm, basically. So that's an interesting question about the forces generated right here. So you're generating this force. Yeah. Well, maybe I might change that back. Maybe bringing it down is not terrible in terms of forces in the system.
Maybe because it's also leaning on like the back of the wheel, so you have caster to kind of help you steer it. Or I'm confused.
We'd have to look at this a little bit more though, to be honest. I mean, the caster in the rear, that's like way more complicated than we're talking about here. Right? Like we're not even talking about.
Oh, no, I meant like the rear side of this wheel.
Say it
I'm
again?
just trying to see if it's.
Oh.
I was thinking about like this wheel.
Oh, this
like,
wheel.
would it be better for you to steer like on the front part of the wheel or behind it?
Yeah, we could steer in the front, but a formula doesn't typically do that though, right?
Well, for packaging, that's the argument you could put it in the front.
Yeah. I mean, you could put it either, but you can totally do either. Baja, we do front steering.
And then the angles of the column dictate that too.
The steering column?
Yeah. Versus like where you steer at, like if you don't hit your angles, we push it more forward, and it makes your angles smaller on your steering column.
Yeah. I mean, I would design my steering column secondly to this. Like this would be more important to me than getting my steering column angles right. I mean, it needs to fit with the driver, right? I would care more about where does this land in the driver's feet, right? Like you don't want this to be up near your under your pedals, right? Because like the steering column can kind of, you can change the angle of it relatively easily compared to the other stuff. It's not as constrained. So I would, if I was going to work the problem, basically, and we haven't even talked about the last issue, which is bump steer. So yeah, so I would first try and get this right and make sure that it meets with your suspension packaging, which is probably also wanting certain dimensions, right? And then that. But yeah, I mean, so you guys could totally make an argument for front steer or rear steer. But just, yeah, that's more, I think, there's also, you get the downside of your front steer that if your front steer, it's exposed for like Baja, right? So it can get hit with bumps. It's not a big deal for formula, I don't think. But I honestly
Oh,
think if you
yeah.
can package in front steer, you can get better, you can get tighter turning. If you can package it in. It's just harder to package in because it puts the steering rack right next to the driver's feet typically. So I think that's so like Baja, we use the rack as a heel stop a lot. I guess maybe it's a little bit in front now, right? You can correct me, Aaron. Is the
It's pretty far in front. It's pretty much like already pushed up against the nose.
so why did we go to front steering? Do you remember?
We went to front steering. Why did we go to front steering? I think because that was before I actually joined the team. But I think Juan, he made the decision to go to front steering because of the issues with going over center.
Yeah.
Because I think the orange car had a lot of issues going over center, and he said it would get stuck a lot. So that's why they changed it to front steer.
Yeah, I mean, but kind of the hard part then is you need to connect to your steering arm up in this area, right? To get Ackerman, if you do front steering, you got to connect inside the wheel. So that's the hard part, right? Is you got to get inside your wheel here. So your inside the wheel packaging becomes more difficult for front steering, but you don't go over center as much, right? Because you imagine this rack is usually up here and it goes over here and over here. So it's like they're almost pointing away from each other. Where here, they're almost already pointing along each other.
Mm-hmm.
So yeah. So there's a lot about. I mean, designing the steering is kind of super over constrained basically. The one thing with this model you have to do, like if I want to change this, it's gonna move I also need to move my rack, right? So what I would do is, so I can say like this is equal to this dimension divided by 2. Right, and so for like a Baja car, let's say we want to make this 60 wide. We make that like 60 wide now, right? And then you can come back and change this.
Mm-hmm.
So we'll now make this 29, so we'll move it 1 inch. Right? 29, 8. Right? So did we go over center yet? And so we already went over center, right? So you need to be.
I didn't know you can move all that.
Right, so it's kind of like a little model steering system basically, right? But that you're right, David. The one thing I did not program in yet was to let you move this point away from the center of the wheel, which you could do. Yeah.
I mean, our sketches don't have that. The ones that I've used and I've sent to Formula as well. They don't. The steering axis is just right on the center. I don't know.
Yeah. That makes sense. I mean, it would, because it might be at an angle, but you might like typically kind of the steering axis. And keep in mind this is 3D, so this axis actually kind of moves in space. So I don't know where you probably want to put it. Where's the steering axis? In the plane of these arms here, right? So you want to like make a cut of the car at the height of these arms.
What I did last time was I looked at like my model, and then wherever it landed on top, I just did the top view of that, and I put a box on your guys' drawings.
Mm-hmm.
I drew it out, but I didn't really like mess with the other things, like the turning and all that stuff. I didn't even know you could make the wheels turn. I just kind of drew over the top.
Okay.
I mean, keep in mind, so what you need to be careful of is, for example, your tie rod could also be hitting this arm. These have to go together in space. So usually this arm is below. This is the bottom arm, it's below, and the upper arm, it's above. And then you also have a shock in here somewhere, a shock or a push rod. So you're tweaking all of this geometry, looking for what's limiting you. And you're trying to get this wheel to really turn as much as possible, your inside wheels to turn as much as possible, but you also want them to converge on this line, so you're getting Ackerman. So I'm going to split you guys up into Baja and Formula. We'll have a little competition. We'll see who can set up a rack, who can set up the geometry here for this. Let's do 50 and do the 50 and 60, and see who can set it up so that you're within 1 foot, so it has to meet within 1 foot front and back of this line, and who can get the tightest turning radius before it goes over center or before the tire hits the arm down here. So let me put you all in breakout rooms. So what's limiting us right now, Aaron?
Right now,
So basically what Aaron's doing, one is he moved the connection point further from the steering axis. So the hard part about that means you have to travel further, right?
yeah, to get the tight
turning, right? Because if it's down here, because the radius is smaller, you can get more turning. But he's also made the rack shorter and pushed it down. But he's still keeping close to Ackerman geometry, so he's keeping his meeting point along this point. So let's see what's your best you can do right now.
Right now, with say 22.
And where's your,
Still,
you're almost not going over center.
yeah, but now we're looking at like 184 in terms of turning radius, and it's still pretty far back. The turning point is behind the axis.
Well, you should at least go Ackerman excessive. That'll help you. That'll help your turning radius. So move it straight again, and then if you move this connecting point, move it up and to the right. So like maybe change it to 40 degrees. Maybe move your rack up too, a little bit.
Yeah.
Because part of the problem is that your tie rods are almost at the same angle as your steering arm.
Mm-hmm.
Moving that up, see what that does.
Let's try that. See what that does for us.
Yeah, let's try that.
See if it still goes to 22.
Yeah, but let's see what your turning radius is.
Go there. That's a little lower actually, about 20 inches lower.
There you go. And you're within the 1 foot now. So let's try something else. Try going 20, put it back straight. And let's try moving your connecting point. Make the radius small. Make it connect still excess Ackerman, but put it closer to the steering axis. So maybe make it like 30 degrees and make the distance shorter. 30.
8.
Go even shorter, go 7. Let's try some bounds and go 25. Let's keep going. I don't know, I like to try the bounds. Let's try make it 25 degrees. Yeah, try making it 6.5.
These?
Yeah. So basically we're gonna make that distance short and then move your rack way up. Move it to like 1 inch from the center line of the front. There you go.
See what that does.
See if it even does. I don't move it that far, but
nope.
But hopefully you don't need to move it as far now. Try 23.5.
About 12.5 or 12 and a quarter.
But you lost 20 inches on your turn radius, didn't you?
Yeah.
Yeah. So that's nice.
Try pushing it. Nope, didn't take it.
All right, well, you guys you're getting close, but I think that's like, I think I would always err on going slightly excessive Ackerman because it's going to give you a better turn radius to meet in the front a little bit. So I'd go even more excessive Ackerman. Go make it 25 again because you're still meeting behind the wheels, right? So
yeah,
move this, move that to like 20. Yeah.
20.
And make that like 0.5. I think it might go a little crazy if you go over the center line. All right, let's try that. See if we can get the tires to meet in front of the. There you go.
And now they're meeting in front.
Yeah, there you go. And you squeezed out another what, 5 inches?
Yeah, something like that.
Yeah, there you go. All right, I'm gonna go bother formula for a little bit. I'll be back.
All right. Sounds good.
Okay, so what are we, how are we looking?
We're looking good. How about you?
Oh man, that thing's turned on a dime, baby.
Get it for them?
you think our car had 3 wheels the way we're turning over there?
Hey, you're good.
We're doing pretty good here. We're playing with the angle between the steering arm and the center line of the wheel.
Oh, there we go.
And
Look at that.
Oh,
How's that looking?
92. That's under.
Casey, did you go over center though? Zoom in. Make sure you didn't go over center. Yeah, see, you went way over center on your right arm. See that?
Center is in this?
Yeah, see how you went over center.
Oh, I got you. Okay.
So maybe
What
you
is
got-
that? What do you mean by that? I don't really understand the over center thing.
Okay, so imagine this point. So
This one?
so this and this are fixed together, like this point where the tie rod connects.
Wait, are we
I
looking at your
can't see
screen?
what you're talking about.
Oh.
I can
Sorry.
only see what Dave. No problem.
There, we go.
Okay, so if you look at this point to let's
Oh, you still gotta.
I still gotta share my screen.
You can't see the screen though.
Point right here.
So
This-
this point to this point, this is all fixed, right? Like this triangle is all part of the upright basically. But
Yeah.
none of this moves. Like this arm can't rotate or anything. It's fixed, right?
Right.
Okay. So this though has spherical joints here and here, the tie rod, so it can rotate. So you watch when let me pull it slower. So what's basically happening is as I'm shifting this rack to the left, this point is pulling this side of the tie rod, right? It's pulling, so this point is pulling this side of the tie rod, which is pulling here. And so you imagine you're basically pulling this. And so as I'm pulling it, keep going. Pulling. Boom.
Oh.
So you see, like you're pulling left. Once it gets into a straight line, it won't pull anymore. So if this part kind of starts to kick, kind of like have a more than a straight angle, that's physically not going to happen basically.
Right. Okay. But that makes it so that if you try to turn back the other way, it'll basically push the tire in the wrong direction.
Yeah. So you'll try and turn right and you'll turn left. You'll turn more left.
At least the right tire will.
Yeah, at least the right tire will. Exactly.
So then what are you saying, Chris, what's the answer to the problem? Because we were trying to approach it by changing this 35-degree angle between the kingpin and the steering arm and reducing that.
All right, let me see what you got. Let me see what you got. Let me see. There's no obvious. The answer is there's no obvious. Let me stop sharing. The answer is there's no obvious solution, but I mean one thing you can do is see you don't want this tie rod to be in line already with your steering steering arm. Keep in mind, I mean, I should, so one thing you should keep in mind is that, so when you turn it, but actually, so you see this, you see that 6-inch steering arm?
Right.
That's actually, you shouldn't actually compare it to this. You should compare it to the line. Can I take it back from you real quick, David?
Yeah.
So you shouldn't actually compare it to this line. You should compare it to the line between here and here. So it's actually steering about this line right here. So like, right? So it's not, this line is totally made up. It's actually between here and here. So we can go a little bit further.
Pass it, or like you can't.
Yeah, that's what you can't go past.
Stay under like the curve.
So I should go a little bit further. So then now I broke it.
Well, Chris, what our approach was, we're gonna move the rack closer to the center line of the wheel.
I think that's good.
And
So it's
then,
almost straight.
and then decrease to that 30 degrees down to, we were about 22.
Okay, so this can actually
Oh.
buckle like this, but the line between here and here, once this gets straight, that's going over center basically.
Right. Okay.
So right now we're about to go over center on that wheel, but we got a nice turning radius here, 114.
And the rack distance is that what, like 2 inches max, or at least for like Bajas?
Baja does about 2, but there's no rule on that. Also, so go back into go back into your drawing. So yeah,
Like
so
this thing that I'm changing, max is like what, 22 inches?
so you can design that. That's totally, because there's a gear between your rack and your pinion here. You can totally change
This
that.
is stuff that
So if you change it to like 1 inch, then you just
You should do it until you go
from
over
here to
center.
here.
But so what you should do is you should look at you can basically moving your rack forward is going to help in this case, because the point between the left side of your, or the point between the end of your rack and the you're basically going to go farther away from going over center, right? So if this point goes up, your tie rod now goes here to here and here to here. So that angle you can travel before, so I'm like, make that 2 or make that 1 inch.
This?
Yeah, make that 1. So now you see the angle between your tie rod and this tie rod connecting point on the left and the steering axis has now gotten bigger. So that's good. You've also done good in that you're a little bit Ackerman excess, so that'll help your turning radius. So if you're gonna air, you want to be a little bit in the front. So let's see how far you can go. So keep going. Go up through 23.5. Oh. Okay. So go back. Actually, you should go. You're still meeting behind the back wheels. So put this back at 25. Oh, what the heck happened here? Wait, chill out. The tire's not straight. There you go. Okay, good. Okay, so move instead of, what's the angle between the 6th and there? It looks like you lost that.
Oh, it's right here.
Oh, okay. Make that lower. Make that like 15. There you go. So that's even more excess Ackerman. So try that. That'll help. So you'll meet in the front, hopefully.
Chris, don't want to keep that that 6 inches, the pivot point of the ball joint right on the Ackerman line?
That's only assuming like a horse and carriage type, like single bar going across, because you can move your rack position now. You actually can deviate slightly from that. You actually want to deviate a little bit because that'll mess with it. So you can keep going, David.
It'll let me after that.
24.25. So do 24.3. You don't need to move much now.
I feel like I should for moving.
22.4. No, too much.
Oh, that's way too much.
Yeah, 20. There you go. So zoom out. So this is, so you're meeting, you have so Bill, you can see he did too much now.
Yeah.
Right? Because he's meeting too far in front of the wheels. So that's too much Ackerman. So he wants to go back closer to the line to put this closer, but he's got a nice turning radius now.
Is it turning right here, right?
Yeah. And you can also, you can try and make your rack bigger or smaller. Make it.
That's what I'm saying.
There you go. This guy gets what he wants.
All right, I'll give you guys another 5 minutes or 5-10 minutes or so.
All right.
Hey, Chris.
Yeah.
All right. Give me a number.
Somebody was talking about making a track width in the back narrower than the front.
Mm-hmm.
The reason some teams do that is so that they can turn the corner without knocking down cones.
Yeah, I mean, it's easier to see your front wheels, so it's easier to avoid cones with your front wheels than your rear. So I would agree. But I think I'm not sure if it actually is better. Like, I don't think a Formula One car would do that.
I don't think so either. I never was in favor of it, but that's what they did.
Yeah, I'd go rectangle. Keep it simple unless you know better otherwise. That's my philosophy. I'm not gonna make it complicated unless I really know what I'm doing.
You see that extra little bit of grit?
Let's see what you got, David.
It's in progress.
I think we made
You made it worse at the end?
Then, you came in and showed us the right way, and then
yeah. Well, we had it down at like 92 or something like that, 97.
For you guys.
we're testing right now. What numbers do you guys hit here?
What's that?
They were high 23s. So keep going.
It's proprietary.
Oh, I guess I hit the magic number.
But you're way in front right now, though.
Where?
So you're 2 feet. Your turning radius is 2 feet.
Oh, that's it.
Or is your turning center of your turn is you're 2 Ackerman excessive.
Wait,
Bring it closer.
I'm too close to the
what happens?
thing?
What happens when you're excessive?
Your some of your tires. So not all of your tires can turn about that point. So
right.
So your whatever tires have less grip start skidding across the ground.
Uh-huh.
And they don't.
Oh, that's good for Baja.
Could be good for
right?
Baja.
So if you're trying to make a car that like drifts or anything like that, where you're like not as concerned about maintaining traction, is it still good to focus a lot on this Ackerman thing? Or
yeah, it's a good question. Or would you favor having more wheel turn? Like would you sacrifice having Ackerman for having a smaller turning radius just amongst your 2 front wheels or something, right?
Right, yeah.
Maybe. This is totally like a how you turn though, like just rolling, right? So it's like we're not really doing much dynamics. The next 20-30 minutes after we do this, we'll have to look at the dynamics a little bit. But I would say it could, yeah. I would say it could. All right, so this is good enough. Let's see what you got, David. You guys got the idea. 118. All right. Could have been 97. Nobody saw it though. No screen grab. All right,
Yeah.
Aaron, what'd you get?
97. Let me see.
Let's see your screen.
All right.
Oh, he probably recorded our.
What's up? Can you guys see that?
Yeah.
Yeah.
All right,
All
put it
right,
back
yeah.
to straight. And let's see where you put your rack. So you shrunk your rack a little bit.
Yeah.
And you
It's about 0.8 from the front axis.
interesting.
Very
You
little.
cut a little bit excess Ackerman.
Yeah.
Okay. So let me just to kind of wrap this up. So let's put my car back to so let's make this a 55. Should have done this in the spare time. Now we're going to see a left-hand turn. So I was actually wrong. I'm looking at this. So when you want to see going over center, you shouldn't don't look at this. Oh, I'm not sharing my screen, am I?
No, you're not.
You're okay.
Buying a nickel for every time I did that these days. So I was looking at this arm versus this arm going over center, but this arm right here, that thing doesn't exist. It's actually turning about this point. So it's actually this arm that will go over center with this arm, which
Right.
basically means when these two arms get in a straight line, you can't go anymore. And you'll see the model breaks at that point for that reason. So what would I do? So what I would do is I would go slightly, so if you keep in mind that for an arc, so if you have a point, you have a body, right? And let's say it had, you know, whatever radius. So you have some radius away. When you want to look at, you know, how far does it go from here to here with theta, right? So if I want to know this distance, let's zoom in. So if I want to know the distance between these 2 points here, S. So we know S is equal to R theta, right? So if I want to maximize theta for a constant distance S, what should I do to my R?
Sorry, say that again.
So my S, this distance that I travel with the rack, right? So I'll pretend like I have a rack that moves left and right. It's gonna push this kingpin, it's gonna rotate it. So if the rack travels a certain distance and I wanna maximize the theta, which I turn this disc, what should be the radius, right? So this is a constant for my rack. I wanna get as much
Make
theta
it
as possible.
smaller.
Yeah, we wanna make this radius small.
Decrease it.
So we want to, so what we want to do then is, so we can make this radius small. Then again, it does make it harder to push it. So you have to get your gearing, your kind of gearing right. It'll also, when we go up further up here, it will also put our rack more in line. But so what I would do is I bring this forward, 0.25, let's bring this, we'll bring this forward. We can try and bring this point 10 degrees. Maybe, oh, let's try some different things. So I would, oh, no, I don't want 10 degrees. I want the 7. So this is too much Ackerman, right? So let's make this
Right.
like 5. And I can make my rack longer to make this angle better. Right? And so now, so if you see that, so that when I make this longer and longer, my tie rod gets steeper here, right? So if I push this point further out to the right, this gets steeper, which goes further away from this angle. So let's see what we got here.
And then if you make that longer, then you're moving that like less, basically, or?
So I can't move it very far now though, right? So let's look. 24.9, right? So I moved it a little bit. $24.7. So it's getting close. It hasn't gone over center yet. 24.5. Hasn't gone over center yet. 24.3. So that went over center. So let's go back. 24.4. 2 24.45. There we go. So now it's almost over center. And so we got around like 98 or so. So we're pushing down those low angles basically, right? So that's that what I would say is kind of, so I couldn't quite beat the expert Aaron, but I got close. But I think that's the basic basic idea. Let's see what happens if I go a little bit down over here. So I'm gonna go 6. So this is true. I'm gonna make this. So in this case, maybe I don't want to go over center so quickly. So let's see what happens if I go down a little bit more. So 18. So I'm going to go a little further away on the radius. So I'm going to make this radius a little bit longer, but I'm going to give myself a steeper angle. Angle. So you see now I have to move more, right, to get the same angles on this thing. Maybe I can get another hair out of here. 23, 23. Nope. It'd be good to have it automatically solve for how far you could go. You see how much time I spent guessing, right? Oh, what now, Aaron? So it was helping. So here I was going. I mean, because I didn't limit my rack travel. It's not really fair because I didn't limit how much I can change my rack. So it was more important to make it so I was further away from going over center to start, basically, right? But let's see here. So now my tire is almost getting parallel with the 30 degrees. So I'm starting to almost hit my arm, right? So this is maybe about as small as you can start to go before you start hitting your arm for this track width. So there's one other constraint we haven't been dealing with. And so if we look at the tire from the back, and here's our, here's our lower control arm mounting points, and our upper, I should make them, sorry, I'm gonna make them a little bit more converging. Right? So we know we can extend these out to get to our instant center. So, and this is kind of the hypothetical point by which our tire will move about, right? So if we want to avoid bump steer, our tie rod has to be moved along with these other arms. Otherwise, if it's not moving with the other arms right, it'll steer your car as your tire goes up and down. So your tie rod, if you draw a line between here and here, your tie rod, when you connect, it should be this length and it should point to your instant center. So tie rod needs to point. So this is our instant center, needs to point to instant center. And be this length. Right? So that's what we did. So we were letting our tie rod length totally change, right? But that's a little bit fixed by our suspension. This problem is totally over-constrained. But there's one thing you can do. You don't need to put it here, actually. You can actually move it left or right. So for example, you could put your tie rod here, right? So you can move it to the left without incurring too much bump steer. So you're fixed on the length and pointing to the instant center, but without taking a big penalty, you can move it a little left and right. But there's programs that will also help you look at your suspension geometry in this angle. Remember that vsusp.com we were playing with? They'll let you also put in these two locations and measure your bump steer, which is a big deal for Baja, right? Because we're hitting a lot of bumps. Okay, so I'm just gonna knock out this last part. So far, everything we've talked about so far is basically like no dynamic steering. We're just rolling. This is like what happens if we roll as slow as possible. So what about like steering dynamics? Like what actually happens when you're going at high speeds? So in this case, we like to use what's called the bicycle model. So let's say let's say the axis of your car is up and down in this plane, and you're making a right-hand turn. So your rear wheel is fixed to your car, so it sits straight, but it has a slip angle, right? So its velocity is actually this direction, right? Your front tire is gonna be turning into the turn, right? And so it points in this direction. So, but the velocity is in this direction. So this is alpha of the front, the slip angle of the front. This is alpha of the rear. This is the slip angle of the rear. So this is going to help you make cornering force of the rear, and this is going to help you make force of the front, cornering force in the front, right? And your car's CG heading. So you also will usually say, where's the CG going? So your CG is going to usually go, your CG is kind of going in that direction, right? So it's kind of a mix. It's a mix of your velocity in the rear and basically kind of the velocity in the front, right? Kind of between those two. Okay, so remember that in kind of the elastic regime of the tire, you guys are gonna kill me. You guys are gonna kill me. So what do I mean by the elastic regime? So you've heard of elastic and plastic deformation for materials, right? And so you've seen where there's a linear relationship between stress and strain, and you call that the elastic region. So we do the same thing for tires. Oh man, this is Baja.
Oh man.
What's wrong with Baja?
They don't have any tire data that they can give me.
Baja, bro. Dude, man.
So if you look at the so let's look at like this tire data. So if we look at this data right here, to get more force, it's linear early on in here. Force versus slip angle, basically, right? So we call so that's what is I forget the name of that term. It's like I forget the name of the term, but anyways, that slope has a name. It's like you know, cornering stiffness, I think is what it's called. Yeah, that's what it is. Cornering stiffness. So if the more cornering you want, you need more slip angle. So you need your tires to slip more and more, right? So you want that angle to be bigger. So if we go and look here, this is going to be equal to the front cornering stiffness times alpha of the front. And this is going to be equal to the cornering stiffness of the rear times the slip angle in the rear. Folks buy that so far? So if we pretend like the cornering stiffness of the front and the rear are the same, that we have the same downforce, we have the same downforce on the tires, and those slopes are the same. And you'll notice those slopes actually don't change a lot with downforce early on. The slopes are here. So you see at like 100, 150, they all have roughly the same slope. So they're not a strong function. That slope is not a strong function of downforce either. So these two are roughly equal. So what that basically means, if your car is turning around, if it's CG's in the middle, so let's look at a neutral steer car. Neutral steering car. Not how you spell neutral, but neutral steering car. So we'll say CG is in the center for this case. And so that basically means since the distance from the front tire to the CG is the same as the distance to the rear, for the sum of the moments to be zero, the force in the rear must equal the force in the front, right? So that means, so, you know, the force in the front must equal the force in the rear.
Can you please scroll down?
Which means, oh, thank you. C front alpha front must be equal to C rear alpha rear, right? So these two forces must be the same, and these two are the same. So that means your slip angle in the rear must equal your slip angle in the front. So when we go up to this diagram, we're basically just saying this angle in the front and this angle in the rear are the same in this case, right? So what does that basically mean as a result? So since both of these angles are the same, and this angle, when we go up, we'll call this delta Acker. So this is your Ackerman angle, right here. This is kind of, or like what we would say, we'll call it the Ackerman angle. So it's basically the tire from going straight. So if we rotate this back tire so that its velocity is going straight, you'll notice that the velocity of the front will go exactly in line with the Ackerman angle. So what that basically means is that you turn in a radius predicted by the angle of the tires. At all speeds. We'll say at all accelerations. Okay, so let's compare what both of your cars typically do. So in both of your cars, your CG, so let's look at your car is what we would call an oversteer car. But typically in your cases, you have oversteer setups. Let's say your CG is 1/3 from rear and 2/3 from the front. So your CG is 1/3 from the rear and 2/3 from the front. So in this case, let's draw it the same. So you have your rear tire. It always points along the heading of your car, or the kind of the axes of your car. So this one is here, but your CG is back here. So for the sum of the, sorry, I gotta remember to scroll down more. So for the sum of the moments in this car to be the same, which force has to be higher, the rear or the front? If you want the sum of the moments on your car about your CG to be the same.
Say it again now.
The rear.
Yeah, so if you want, so pretend like you have a force in the rear pushing it in and a force in the front pushing it in. If you want them to be equal about the CG, then the force in the rear has to be higher, right? Than the force in the front. An interesting part of this argument is that this force is not necessarily perpendicular to this distance. So it'd be interesting interesting to analyze how that angle affects it to do a more detailed analysis, but this is complicated enough. So let's say, so in this case, I mean I think this angle is way larger than it probably actually is, right? This is 2/3. So in this case, we have force in the front. It's equal to the cornering stiffness of the front, alpha of the front. We have force of the rear times cornering of the rear times alpha of the rear. So in this case, we have some velocity of the front. We have some velocity of the rear, right? And then you have the velocity of your CG. Okay, but in this case, we said the force on the rear must be equal to 2/3 the force on our front. Sorry. 2 times the force on the front, right? That's because this is half as far away as this, right? Okay, so if this is equal to the cornering the rear times alpha in the rear, right? And this is equal to 2 times the cornering in the front times alpha in the front. And we assume that our cornering stiffnesses are the same. That means the slip angle in the rear is double the front. Right? So we need twice as much force in the rear. We need twice as much slip in the rear. It has to be slipping twice as much. Right? So what that does, right? So let's pretend, and so the total, so the kind of the force total is basically equal to the cornering stiffness times alpha front plus alpha rear, right? So, right, because the corner, so in this, and if we want the same, if we want the same total amount of slip ratio in this case as we did in the other case. So let's say last time we did 10 degrees, let's say last time we did 10 degrees and 10 degrees. So in this time, instead of 10 and 10, we'd have to do like 13 and a, we have to do 13 and a third and like 6 and 2/3, right? So before, if we did like 10 degrees front slip and 10 degrees rear slip, right? So we had even. So we want to do the same acceleration turn. So in this case, we have to do 4/3 that amount in the rear and 2/3 in the front compared to before. So we need to, so right now, so we want the same total amount, but we still need this, right? So if we still, so I still want the same total amount of slip, but I need the rear to be twice as much. So compared to before, I need 4/3 more in the front here. So I need like 13.3, for example. So this is the, this was our neutral steer case. And now we need like 13, or we need like 6 2/3. So what's, yeah, 6.6666, yeah. In the front slip, and we need 13.3 rear slip, right? So now our rear is slipping a lot more, right? So what that basically does, when we come back up here, and we analyze this, if we put this where it was before, what we basically have to do, this is 1/3 more this direction. That's 1/3 more this direction, right? And that'll bring it in line with the old vector, right? Because we know this one's 4/3 what it was before, right? And this other one, right? This front, it should only be. So what that's going to do? That's going to move this vector. That's going to move this vector 1/3. Right, so that's going to move. So if we rotate this, so it has one more, we rotate it back even. That's going to bring this 1/3 more this direction. Plus, this vector is already 1/3 less. So we have another 1/3 from the front, and another 1/3 from the rear, right? From this vector. So what does that mean? What am I trying to tell you? So what I'm trying to tell you basically is that the oversteer car, to get the predicted turn like you would before, we actually don't need this vector to be so far to the right. We can move, because this front vector is moving 1/3 over, 2/3 over, you can basically take your Ackerman, and so for oversteer, move it 2/3, right? Move it 2/3 of alpha from neutral steer. So basically oversteer car, to get predicted turning, of neutral steer less wheel turn. And so kind of the issue with this is this can basically get worse as you accelerate more and more, right? So because as you accelerate, as you want to do harder and harder turns, you need larger slip angles, right? So what basically, so you'll hear, I mean, so if you watch like a Formula One, they'll be like, man, this car's oversteering like crazy. So imagine what that's like. So you're driving, and you're coming into this turn, right? And usually you're turning harder. You're turning more and more cornering as you get closer to the corner. And what's basically happening is the car, as you're turning hard to the right, it starts digging more and more into the current corner. And so you're having to continually, as you turn, to stay on that turn radius, you're needing to turn your car further and further out, right? So imagine the frustration you kind of have when you're like, you think you're on this line of you're turning in around, and you're thinking on that line, and you keep going further and further in. And so you're having to fight it back out of the turn, basically, right? So that's why you hear the drivers, they're kind of, it's a totally a dynamic effect, but it's basically, it happens anytime you have this oversteering issue, anytime your front is kind of has more ability to kind of like to have traction than the rear does. So, and this will happen. This will happen when your CG is further in your back, basically, too. So you would prefer to have understeer, which is you kind of like think you're going into the turn, and you keep moving a little bit out, and so you just have to go a little bit more in, right? So that's like a little bit more stable than like, oh, I think I'm making this turn. Oh, I'm going too far in, right? And you're kind of back out of your own turn, basically, right? So ideally you want, a lot of people will, so you basically, yes, and this gets worse with total cornering forces or accelerations, as alpha of neutral steer goes up, basically. Right, so this happens anytime we'll just say cornering ability, for lack of a more technical term, in the front. Just basically means you have the ability to do more cornering in the front. So like, and so a lot of times you'll do a lot of different things to change your setup so you can get your car closer to neutral steer or slightly understeer. And I've heard some arguments that you want a slight bit of a slight bit of understeer, so like you have more capability in the back, because one, it's more stable, and two, it allows you to accelerate out of the turn, basically. It gives you a little bit of extra grip in the rear to not use for turning, but instead to use for acceleration. I've heard that. I've never done this in practice. The Baja, we do a lot of oversteer because we have a rear differential, we have a rear solid axle. And so our wheels can't spin at different rates in a turn, our rear. So they suck at turning. So we say, screw it. Let's not have the rear wheels turn. Let's just whip them out, right? So that's the least, like, that's basically what I see with a lot of the Bournemouth teams. When they do tight turns, they basically just rip, they just let their rear not do any of the turning and let it fly around. So that's one reason to make it narrower. So let's see here. So
I think another reason why they would have the kind of favor the understeer or oversteer is because there's a thing called snap oversteer, and it's probably when you have a really well balanced car and then you're hitting a corner and you hit the limit, but if you're not experienced, you don't really see that limit, so you might just pass it and it'll just like kind of mess you up.
yeah.
And I think that's like a 50 balance, basically, like a neutral steer, right?
Yeah.
It's like everything's even. Okay.
Even. Yeah. And yeah, I mean, it's a little bit different too, because it's like, I don't even know if you'd consider it oversteer, because they're like losing traction in the back. They have like no traction. But anyway, so if you want to like reduce understeer, right? Like you're not getting enough turn. All of these things basically want to do is basically increase increase your turning ability in the front, basically. So like you can either like get a little higher tire pressures to help you corner in the front. You can, or let's see, so reduce understeer. So here you're trying to oversteer more. I always get confused with this. So you're trying to oversteer. Yeah, so you're trying to get more grip in the front, right? So you're like widen the front track, right? You can soften the front shocks. So you can, when you think about softening the shock front versus the back, so imagine in a roll, your car's kind of rolling. So it's pushing on the front left springs and the rear left springs, right? Imagine you're rolling, you're pushing on the springs. If your springs are stiff in the front, you're gonna have more of that weight transfer into the front, which is gonna make it harder which is like having a kind of a front heavy car. So you actually wanna stiffen the rear shocks because that's like having a more like weight in the back, right? So this softening and stiffening the shocks is more about like translating it. But you can see, so and like sway bars, for example, right? Sway bars are like help you be really stiff and roll, but not in bump, right? So basically, there's all these little things people do to kind of tune their car in, right, to get it steering right. And so this is like working a lot with the driver feedback, basically, right? And then going in and making little adjustments. So you can see like stuff here like, increase the front negative camber, right? So they think they have some camber thrust, basically, right? So I think that's, for the most part, what I want to talk about with the steering. Sorry, that was 2.5 hours. I know it was a lot, but we covered a lot, right? So we talked about understeer and oversteer, kind of dynamic steering, right? We talked a little bit about being deficient or excessive in Ackerman. So here you can draw a line from both sides and see where they meet neutrally, or you can just say it doesn't meet inside or outside. We talked about the steer angle in the front has to be a little steeper, right, to get those things to match. And so that's why we set up the Ackerman. We didn't talk as much about how the rack and pinion works, but we talked about the different components, right? And then we talked just kind of at the beginning a lot about just the different angles, toe in versus toe out. You want to have a little bit of toe in. We talked about what camber is. That was more last time though, that we want pretty neutral camber. We said that we want a little bit of trail, right? We always want this steering axis to come in front of where the tire hits the ground, right? And we said we usually want a little kingpin inclination, right? Like 5 degrees to make it stable, right? And we typically want, in Baja, we usually have like 1 inch or 2 of scrub radius, but we don't have much scrub radius on the formula car, right? But so I know that was a lot. We really killed it today. A lot of physics, and we saved the worst of it for last. But so I'll post this video. I'll post that Solidworks. So if you want to mess with Solidworks or you want to try and make a front steer ever, it's in there. The quarter car simulation's in there too, if people ever need it. But that's a little bit about what you're thinking about with the steering and bump steer and that sort of stuff, right? And the bump steer also happens in the rear, right? So what we were talking about for the we were talking about for the tie rod in the front, it's true about your toe link in the rear, right? Because otherwise your toe link will make you steer in the rear for like a formula car, right? Aaron, did I miss anything critical?
I think you covered most. I think you pretty much covered everything.
We got it mostly.
I think so.
Any last things I want to say about there was one last thing. So one thing to keep about is the gearing of your rack and pinion, right? So one issues we've had before on the Baja team is to turn. To get that turn, they had to turn their hands all the way over, right? Which you can't do. So you should keep in mind, you also need to think about the gearing of your rack and pinion. So your driver is only maybe going 90 or a little past 90, right? So don't forget that your driver is doing all this, and they should not have to go hand over hand in a race car, right? Going boom, boom. It will make it harder. It will make it harder for them to. It will make it harder for them to turn because if they don't go very much, But so you want to use about 90, right? So it makes it easier for them to turn. And the steering wheel, you don't want it too close because then it's high forces to get the moment. So you want it far enough away that it's not like unergonomic. Like you don't want a bus wheel, but further away is good because it means less force to get the same moment, right? That was the last thing I wanted to say. I promise. Any questions about any of this stuff?
When do we meet again?
So next Tuesday, I think we have the pleasure of talking about the drivetrain next Tuesday. So we gotta get to the good stuff. We've talked about what's possible if drivetrain does it right. So we'll start to talk about, well, what does drivetrain have to do right, basically. This is tough because Baja and Formula, this is maybe one area there where they're more different. Like so far, a lot of the similar principles apply, but in the drivetrain, one uses a CVT and one shifts. So, and Baja's going to 4-wheel drive. So I'll try and make it general. It'll probably be a little shorter. I think it'll be less, maybe like less technical, I would say. I probably won't do an engine session. I think there's too much to talk about with engines in general. And I talked about it in that meeting one time, kind of some of the fundamentals. But yeah, I think so. We got to talk about drivetrain and
What about camber change with steering and caster?
camber change with steering. Oh,
Yeah, like
I would probably avoid it.
okay.
I mean, you want your tire to remain upright at all times. So I don't know why you'd want. I don't know if you'd want to camber your tire.
Well, it's camber change with and how that affects with caster and for the front steering.
Camber and
Correct.
caster.
Yeah, so you go in the corner and you have camber change, and then you're also turning your wheel, and how that helps you or benefits you. I'm sure it's like a MATLAB code you could pop up.
I don't know. I think you guys have enough to worry about, right? I mean, it took us 9 months, and we had our wheel running into our A-arm, right? So let's get the basics right, and then we'll go on to. We can go on to what should the caster be at a 5G turn, and so I'd let's get the basics right. Let's get it built and let's test it. But it'd be interesting if we could talk about it technically. I'd be like, but I think it's really hard to say like. I mean, it's even hard to talk about all the angles when the car is just sitting still. More or less, when you start to turn the tires, right? And then the car starts to roll, right? It's like the angles really get nasty. But I think the basics are probably still the same. You want the tire to be vertical in those scenarios, and you probably still want some trail. So you don't want like your trail to go away in those scenarios either. But yeah, I don't think you're. But yeah, I mean, this stuff is dynamic, right? Your suspension arms are moving up and down. So if through travel, these things will change, right? Your caster and camber will change. But we talked about you want some negative camber through travel. I probably wouldn't have my caster change that much through travel. Just off the start. I mean, I don't see I've never seen a solid argument for why to do it. So for me, it's keep it simple unless I know otherwise to try and make it more complex. Anyways, we'll let the rest of the folks get to dinner. All right. Well, thanks for everyone for tuning in. Let's see who we got here. Who gets brownie points? We got Aaron. He's been a regular. Hobby's dominating. Jocelyn's dominating. We got Nick. Good to see him back. Tyler, Calvin. We got a regular crew here. Looks like we already know our leads for next year.
Is Calvin on his cell phone?
You still here,
Yes,
Calvin?
Calvin.
Let's see if he actually gets credit.
Yeah, I'm here.
Oh,
What
Okay.
what is our car, Calvin? Oversteer or understeer? Or neutral?
Neutral, baby.
That's the goal.
All right. Well, stay healthy, everyone. Tyler, you gonna get a real section next year?
Nah, I'm trying to look into aero stuff.
Oh,
I'm just interested in it.
All right. Well, Tyler's gonna do an arrow lesson to finish this workshop series up.
Cool.
All right. See you, everybody.
All right.
All right.
Later.
Bye.
Thank you.
Bachman.
No problem.